welcome to the lectures on modern digital communication techniques. So, we are discussing signal processing at the receiver, mainly the equalization, by means of which we are able to cancel the effect of the channel. So, we specifically chose the word cancel because we want to cancel out the echoes which the channel produces. So, just to remind, whenever we have an impulse into the channel, there is a channel impulse response, which can be viewed as multiple echoes of the transmitted signal. At the receiver, these echoes cause intersymbol interference. So, if we pass the output of the channel through another filter, which could cancel the echoes, so that effectively we get the output as an impulse, the effective output of passing the signal through the channel through the equalizer would be an impulse itself. So, the impulse response, if it turns out to be an impulse, then there is no ISI, and we had seen such a filter in the previous lecture. So, when we consider channel equalization, one of the important things we should note is that it requires knowledge of channel. We said that channel equalization coefficient should be equal to 1 upon the transfer function of the channel as one of the realizations. So, the natural question is, where do we get this channel coefficient from? So, this channel coefficient should be acquired by means of channel estimation techniques, which we will explain shortly. So, when we look at channel equalization and channel estimation, the channel estimation part can be broadly categorized in divided into two methodologies. One is the data aided, one is the data non aided, that means no data aided. The data aided means there is pilot or prior knowledge about the transmitted sequence, whereas in non data aided we do not use any prior knowledge about transmitted sequence. With pilot, what we mean by ideally an impulse, we mean to say that if the training sequence is an impulse, the response of the channel is an impulse response. So, if I send an impulse which is a known sequence, I can easily capture the impulse response. However, an impulse has a very high peak to average power ratio, and transmitting an impulse is a real problem. So, generally people work with pseudo noise sequences, which has a channel transfer function whose gain spans uniformly across the available bandwidth or the bandwidth of interest. So, we generally use a PN sequence, and this same PN sequence is also used for synchronization techniques, we will see shortly. So, the design of training sequence is a very critical activity, and it is a very important task, and it helps in designing better communication systems. Non data aided means there is no additional data requirement for channel estimation. From whatever received signal is available, one could estimate the channel coefficients. These techniques are naturally spectrally efficient because no time or spectrum is wasted for transmission of pilot. However, it has limited performance compared to a data aided, and it is complex in nature. Our focus on channel estimation, what we discussed, would be primarily data aided. However, just a brief note, when we move on to synchronization and other techniques, we may take a look at non data aided, when things will be a bit clearer. So, in terms of equalization, there can be various forms of equalizer, and one of the forms of equalizer that we would be interested in is the linear transversal filter. So, by transversal we kind of mean a tapped delay line model. So, we consider an impulse response where the channel impulse response does not go to 0 at the sampling instance adjacent to the main lobe. So, this causes intersymbol interference. So, that means the response, if I launch an impulse into it, I can get responses something similar to that. So, at sampling instance these do not go to 0. So, these are basically echoes of the main lobe. It is the same signal, but echoes coming at different instants of time, and so on. So, to achieve raised cosine overall transfer function, if we keep H equalizer transfer function as inverse of the channel transfer function, so that the equalizer times the channel gives a raised cosine, we are satisfied. Since we know, as we have discussed, the transmit filter can be root raised cosine, the receive filter can be root raised cosine. So, this would give a transfer function of 1. So, the transmit along with the receive when taken together would give a raised cosine. So, this equalizer basically cancels all the impulses. So, we briefly discussed this. So, if there is a channel, if we send an impulse, the response would be something like this, and we want to fit a equalizer which will produce finally an impulse. So, if it produces an impulse, in that case all the echoes, these echoes have been forced to 0, this echo has been forced to 0, this echo has been forced to 0, you are left with an impulse. So, combined transfer function, that is when HEF multiplied by CHF is equal to 1 in the frequency domain, which is equivalent to impulse in the time domain, since it pushes all the interfering pulses or the echoes to 0. This is also known as the zero forcing equalizer. So, the output is typically convolution of a signal with the coefficients. So, you could find the coefficients as inverse of x times z, and this procedure could be used for both the estimation of the channel coefficients as well as of the identification of the received signals. So, when you estimate the channel coefficients, we will have x as the known signal. When we estimate the signal coefficient, the signal values, in that case in this model x would represent the channel estimates that we have already acquired. So, in the process of channel estimation and equalization, we can model the received signal in the form y is equal to h x plus w, where w represents the noise, h represents the channel matrix, which could be looked upon as the convolution matrix, and x is the vector of transmitted signal, and hence y is an outcome of the convolution matrix times the transmitted signal. So, this ensures there is convolution. As a first step, we are supposed to estimate the channel. So, we can look at the noiseless signal, which is y equals to h x, and one could estimate the channel coefficients in this form if x is known. Now, since invertibility could be an issue, in that situation one could use the pseudo inverse and one could acquire the channel coefficients. So, this x which is known at the receiver are basically the pilot or the training data, which we discussed earlier when mentioning the data aided channel estimation. So, once we have estimated the channel coefficients, one could go to the next step when there is data transmission, that means x is unknown. In the previous case x was known and we could estimate channel. Now, x is unknown and one would estimate x from observed y using this expression, when h here would be the impulse response and not the convolution matrix. So, depends upon how you write the expression. In the least square sense, the expression of the decoded or the estimated symbols would be this, where h would be the channel impulse. So, when we estimate symbols, we use h estimate, which has been acquired in the channel estimation process. So, it is a two-step procedure. First you estimate the channel, followed by equalization, so that you get back your signal. In both the situations, we see a lot of similarity in the way the expressions are used, and hence one could think of using the zero forcing algorithm for channel estimation as well as for equalization, or one could use different algorithms in the channel estimation and equalization. We will see some more algorithms which will talk about estimation of signal parameters, which could be used in either channel estimation or in equalization. A side note at this point is important. So, when we consider this kind of an equalization, we have said that we will use 1 upon Cf as H equalization, which is the zero forcing equalizer, because together when we see the transfer function, it produces a 1 in the frequency axis, along the frequency axis. So, we are taking inversions of the channel transfer function. So, if the channel transfer function has a response which goes like this, we are definitely taking the equalizer coefficients where wherever there is a high value, it is a low value getting multiplied with this, so that you get a 1, and wherever there is a low value, H e of f should be a high value, because together it should produce a 1 over here. So, if we look at the expression here, what we could guess is this kind of a multiplication with the received signal would also get multiplied by the noise. So, that means H e f would also multiply the noise. So, that means whenever H e f is high value, noise would get enhanced because of high value of the channel transfer function at certain values of frequency, and that happens wherever the channel has a transfer function with low values of frequency. This phenomena is also known as noise enhancement, right. So, with noise enhancement, with this kind of equalization, one encounters the problem of noise enhancement, and this is primarily because we want to force all other echoes to 0 and keep only the impulse at the first place. If we would have relaxed this condition, then things could have been better, and there are different receiver equalization algorithms which do not necessarily force the interference to 0, but allow a slight amount of interference, where even then the communication achieves a good performance. So, to discuss channel equalization further, we need to look at the general class of linear optimum discrete time filters, which are known as Wiener filters. In such a model, we have a sequence of input, and there is a linear discrete time filter with weights w's. The output produced is y, and there is a desired response. So, we may desire an impulse out of it. We can produce any sequence, and it has therefore an estimation error, because these may not be exact, which produces the desired response. And the reason is these have noise in it. So, if it has noise, we can only find these w's up to a certain accuracy. So, the requirement is to make the estimation error as small as possible in some sense. That means, small in the sense of what is the question. So, generally we use the criteria that the mean squared error is minimized. That is one of the major and important criteria that can be used. So, there are two restrictions on the filter, that we would like the filter to be linear, and we would also like it to operate in discrete time. The filter, if it is linear, would help mathematical tractability, and if it operates in discrete time, then we will be able to implement it in hardware or software. That means, we have the power of DSP with us to implement the receiver. There is another set of literature available which can help us in building such filters, which is from the Yule-Walker equations. So, there also we have R as the covariance matrix of y, and in that case our optimum filter wave coefficients could be calculated using this expression. So, we proceed with this knowledge. The next set of interesting relationships which matches our requirement are the Wiener-Hoff equations for linear transversal filter. So, that says from orthogonality principle the input must be orthogonal to the errors, we will see more of it, right. So, that the weights that we choose ensure that the inputs are orthogonal to the error, that means the inner product would produce a 0. So, it assumes that the input goes through a linear transversal filter whose coefficients we have to find. So, there again the coefficients can be found using these relationships. So, they all give us the same kind of result which we can exploit in finding filters which will produce the desired response. That means, it will produce an error which is minimum in some sense. So, we move ahead with this to discuss the mean squared error criteria. So, we have the output y as per our model, which is the convolution of the filter coefficients with the inputs, that is what is expressed over here. We want to find the filter coefficients that would produce y which is as close as possible to the desired output. So, we will assume that u and y both are 0 mean, which is reasonable in our case because noise is 0 mean and the constellation we have taken are mostly 0 mean. If you take PAM, it is 0 mean. If it is QAM or QPSK, we also take 0 mean, and we have discussed when we talked about spectral characteristics that is desirable to have a 0 mean. So, the error is D, which is the desired, minus the output of the filter, and we use the cost function which is the expected value of the error squared. So, which is written over here. We consider in general the weights or the filter taps to be complex, that is A k plus j b k, and in that case the del operator would have these expression which is again from calculus. So, our objective is to find the weights which would minimize this objective function. That means, we should take the derivative of j and set it to 0. Now, weights are complex. So, therefore, we have this del operator in the complex notation. So, we should apply this on j, set it to 0, and the result should be able to give us the weight coefficients. So, that is what we have stated over here. So, we take the del operator on j, so that we want the weights which would find the minimum value of j, and we set it to 0. So, after a few steps of operation which is stated here, which is not necessary for us to describe in details at this point of time, we can focus on the set of outcomes that we get. What we get is that the output of the filter, when it is optimized, is orthogonal to the error that the filter produces or the outcome of y with respect to d. So, we should be able to use this result in deriving the weights that we require. These few steps one can derive, or one could concentrate on the final outcome of w that we get. So, when we talk about this orthogonality, we in other words mean that if we have an input and we have the output of the filter, the error which is the difference between the desired and the output of the filter should be orthogonal to the output of the filter. So, we can use this geometric visualization to get to our weights that we require. So, if you work that out, the solution which one reaches looks a bit cumbersome, but this is what we generally use as the MMSE equalizer in most of the communication systems. So, we have, suppose we write the expression as x equals to sum h theta plus w, where theta is something to be estimated. So, earlier we had written y equals to h x plus w, but we have changed the notation because generally all estimation problems are described mostly with this theta as the parameter to be estimated. So, h is the set of coefficient or the matrix which relates or which maps these parameters, and this together forms the signal model. This is the noise. So, we can think of this as the input data, this as the convolution matrix, and this as the outcome or the output at the receiver when this is the noise, right. So, we have a similar expression there. So, the estimation outcome is the expected value of theta plus the autocovariance of theta times H Hermitian. So, if H is the channel matrix, it is Hermitian. Inside you again have H times the autocorrelation, autocovariance matrix H Hermitian, this is the Hermitian operation, and then this is the covariance of noise, which can be the noise power and the identity matrix, inverse of that times y minus H e theta. And for this, one is referred to the book on statistical estimation theory by Stephen M. K. There are a lot of details about it given in that particular book. So, if you are very interested in pursuing the details as discussed in the previous few pages, of course, we will not ask you to reproduce these derivations, but it is important to remember the results that it produces, the notion or the kind of receivers that we get. The details of this can be found from Stephen K. and the books on adaptive filter theory by Simon Hakin, as well as a lot of lecture notes by John Chioffi. So, if we make E of theta equals to 0, then this term vanishes as well as this term vanishes, and one would be left with E. One could easily write this as expression given here, which is the very well known and celebrated expression of the MMSE receiver. So, what we have over here, if we have R theta theta as identity, we have H H Hermitian. So, if we look at this matrix in a little more details and we say, let us say this is identity, what we have with us is H Hermitian, H H Hermitian plus let us say I, and of course, there is 1 upon gamma and y. So, if we remove this term, suppose we remove this term, what we are left with is H, we take the inverse operator H Hermitian inverse H inverse y. So, what it produces you see is that H Hermitian times H Hermitian inverse is identity. So, we are left with H inverse y. So, we are left with H inverse y. So, that means, in an extreme case this boils down to a zero forcing receiver. So, the difference from a zero forcing receiver that we have over here is it introduces this vector, this particular matrix, which is the covariance matrix of noise. So, that means, if we focus on the inside of the inversion, we will find that there is some H invert available, but it is restricted by 1 upon SNR, because there is the noise variance, there is R theta theta which controls the power of the signal. So, if I take R theta theta out, I am going to get R theta theta inverse over here, which would effectively cancel out with R theta theta, and here we are going to have R theta theta in the denominator. So, if R theta is an identity matrix with some coefficient signal power, that is variance of theta. So, we are going to have variance of noise upon variance of signal and an identity matrix. So, we are going to have 1 upon gamma and I. So, this restricts the minimum value to be achieved. That means, we said that equalization is C of f, which is equivalent to C inverse. So, here it is H, both are identical. So, we are restricting this to some minimum value. Instead of saying C inverse, we are restricting this to a value 1 upon gamma inverse. That means, if C goes to 0, that means when C is very small, the H EQ is very large. So, when C is very small, it goes to 0, the inversion becomes very large. So, we are restricting it by this parameter, by this number over here. So, if C is very small, the inversion will not be very large, because it is restricted by the 1 upon SNR parameter. So, it restricts the noise enhancement, which was a typical problem in case of zero forcing equalizer. So, we usually go for this kind of an MMSE receiver. However, a side note for those who are very keen with these kind of receivers, these kind of receivers generally do have a bias. So, one may be required to remove the bias, but at very high SNRs, the performance of this receiver is comparable with that of zero forcing, when inversion of zero forcing is not a problem. If inversion of zero forcing receiver is a problem, then they do not compare at all, because in case of zero forcing, the matrix does not get inverted. Well, just one point to remember, if we are using the pseudo inverse, you can invert it, but there will be huge amount of noise enhancement. The next method that we would like to look at is known as the method of steepest descent, and this uses an adaptive technique instead of single shot. So, what we see in this receiver, it is a one shot estimate of theta. So, in according to our earlier slides, we get the weight vectors W directly by this computation. So, it requires one to wait till one receives good amount of y, right, or good amount of x over here. Okay. So, one to use adaptive methods, because we could continuously improve the performance, as well as we could continuously use tracking methodology to pursue the equalization build up, whereby we may reduce the demand on the pilot data that may be necessary. It is a gradient based approach, and it is recursive in nature. So, we start with consideration of the cost function g of w. However, we consider g of w, which is continuously differentiable. So, w is the weight vector. So, j is a function of w, we have described before, and j w maps the elements of w to real number, because it is the mean squared error. So, w is complex, but still this is a real number, and we want to find the optimal solution w 0, such that the cost or the mean squared error with these optimal weights, or w o, is less than any other weights that we decide. We can clearly see this is an unconstrained optimization problem that we are handling. So, we can think of a situation where there is input and there is a plant. It is a typical model for channel parameter estimation. So, in case of plant, we can think of a channel, right, which produces an output, and we want to find the weights adaptively, so that the signal, when passes through this, compared with the desired signal, produces an error which is minimum, and we will be able to drive these weights using these errors, so that y comes as close as possible to d. So, in this way we could estimate the channel coefficients in w. The other version that we can have is the input signal goes through the channel, passes through the equalizer filter, and we have y. The other path would be the delay, which means that I would be able to store the signal at my receiver, which is d, that is the pilot. I will compare the output of the equalizer with the desired signal. The errors that I get will be used to drive and find the weights of the equalizer filter directly. This kind of a system is known as inverse system identification, because we would like to invert the effect, we would like to equalize the effect, so that here we produce the desired output. Using whatever we discussed earlier, we would like to get an impulse, that means 0 ISI output here. So, with this we stop this particular discussion, and we would like to continue with the kind of equalizer that gets built with these kind of configurations which are adaptive in nature. Thank you.